So before I start, I'd like to acknowledge, my students and my colleagues in Leiden, and also my collaborators at Tübingen University in Germany. This is the group of Reinhold Kleine and Dieter Kölle, who are now helping me characterize my squid and improve their performance. Okay, but why would you want to print squids? What's the advantage? Well, for me, the motivation was because I needed this in my own research lines. You see, my research usually revolves around superconductors with exotic pairing symmetries. Now, this could be unconventional materials like this strontium bruceinate, the crystals you see here, or superconductor ferromagnet hybrids, as well as other correlated electron systems. But one thing, what I was missing was that in addition to my normal transport measurements, I needed a way to probe the local magnetic fields. So, for instance, here in this microstructured strontium bruceinate rings, theory tells me that because of the breaking of time reversal symmetry, my superconductor should be a local but finite field coming out of my superconducting ring. And well, of course, how do you measure such fields? Well, there's no doubt that squids would be the ideal tool for this. However, there is a catch. You see, as I'm sure you're all aware, so far the fabrication of squids is solely relied on thin film deposition and lithography techniques. And this is, of course, a multi-step procedure, and it can be invasive. So you need to often dip your sample in solutions and bombard it with ions. But more importantly, this is only compatible with planar structures. So you need a flat substrate, which is not what you have, what I have in most cases. So it would be, and I think I'm not alone in this, we needed a way to be able to print these devices on arbitrary structures with arbitrary configuration and even fragile structures. So, to do this, I decided to use the technique known as electron beam induced deposition. In this case, the whole process takes place in a scanning electron microscope, like the one you see here. And it's because of using electrons, this is very non-invasive. So you're only exposing the sample to an electron beam. Now, the way that EBIT works is that you inject some form of a precursor molecule, usually a metal organic compound, into the microscope chamber. Now, these molecules are stable until you expose them locally to a focused electron beam, at which point they dissociate and form a deposit. In our case, that would be tungsten carbide. And of course, if you go out of plane and you scan the beam, you scan the beam carefully, you can even make 3D structures with this. But EBIT is not a new technique. It's been around since the 90s, and people have used it to make these fantastic looking structures that you see here. However, unfortunately, when it came to the electrical properties, these materials, the deposited materials, turned out to be, not very useful. Because you see, and this is a common problem in with all printing techniques, that the deposited material is highly disordered and has a poor electrical conductivity. So, and especially at low temperatures, this gets a lot worse. But if something is not a good conductor, it can be a very good superconductor. And tungsten carbide is an example of this. So there were a lot of efforts to make superconducting tungsten carbide using this technique. Unfortunately, however, most of these studies found no sign of superconductivity. And what you see here is that as they go down in temperature, you see that the resistance just shoots up, and there's no superconducting transition. In fact, when we started, there was, however, one report where the authors succeeded to make superconducting tungsten carbide, but the transition temperature was about 2 Kelvin. And this was widely believed to be the limit of what you can do with this EBIT. And 2 Kelvin is a bit of an awkward temperature, maybe, because most cryostats usually you go to at least to 2.1 Kelvin. So it's not a very, it's a bit of an awkward temperature. But we decided to give it a go anyway. And my bachelor student at the time started printing tungsten carbide wires, like the ones you see here. And of course, one day he managed to make a wire which had a transition temperature of 3.5 Kelvin, and which was already higher than the previous reports. So when we looked into it, we found out that what Tycho has been doing, what he was doing was that he was using a much higher beam currents than the previous reports. And I think that was the main breakthrough. So we realized, you see it also here, the resistivity for different wires deposited with different beam currents. And you see that you go from metallic with non-superconducting, but metallic, to superconducting. And we managed to boost the TC up to 4.5 and even 5.5 later. One thing you should also notice is that by increasing the beam current, we also see an increase in the tungsten concentration in the deposited material. So that also is a signature of what we're doing, what we did differently, maybe. So the bottom line is that we managed to boost the temperature to 5 Kelvin or 4.5 Kelvin. But more importantly, we noticed that by adjusting the beam parameter, we can tune the electrical properties of this tungsten carbide. So, for instance, if I scan the electron beam slowly, I would make superconducting tungsten carbide. But if I do a faster scan, then I make metallic but non-superconducting tungsten carbide. And this provided us with the means to make our Josephson devices. So this is how we did it. First, we printed 2 superconducting wires with the slow scan, which were separated by 160 nanometers roughly. And then we connected them using this metallic but non-superconducting tungsten carbide to create the weak link. And this is an image of one of the earlier Josephson junctions that we made. And of course, later, here I'm showing you the Shapiro step. So this is the response to microwave radiation. And here is the response as a function of microwave power. But it's clear that we have Josephson transport. And but what I want to show you, and it's perhaps more interesting, is that we found that by tuning the beam parameters when depositing the weak link, the non-superconducting part, we can actually control the non-superconducting current of our junction. We can actually, if we deposit it, let's say with do a faster scan, let's say small dwell time, we'll always get a critical current of about 4.5, 5 microns. But if we do it with the 10 millisecond dwell time while scanning the beam, then we can actually boost the critical current to somewhere around 40 microns. So this is, again, it gave us a way to tune the critical current and also resistivity of our weak links. And this, I must say that the junctions are surprisingly reproducible. If I use the same parameters, I always get the same critical current. And this is quite unusual for something that is so disordered and deposited at 10 to the power minus 5 millibars in a microscope. But compared to the junction, they were a little bit less reproducible, and there were some asymmetries in the junction. So we decided to actually change the junction. We decided to actually change the design. So I'm now going to show you the second generation of these junctions. So my student just actually managed to take the first squid with the new design, which is miniaturized and also has a, you don't need to apply a magnetic field. You could just use a passive current through this one of these lines to tune your squid. And this, of course, substantially reduces the area of the squid and also improve the area transfer function. But it's being measured as it is now. But the bottom line is that we also managed to reduce the area by at least an order of magnitude. And finally, I want to also mention that one of the big advantages of this technique is that you could use it to print 3D structures. And my student Nick is currently working on this, and we see already that we have a superconducting transition, which is encouraging, but it's not quite optimized yet. So we hope to be able to also get homogeneous 3D structures using this technique. And with that, I'd like to thank you for your attention. Any questions? All right.
Occurring because of there is in the there should be voltage. The potential difference, and what effect causes this voltage in your sample?
Okay. Well, first of all, so there's two regimes. There is the Josephson junction.
What type of current do you have? AC or DC? Is it?
Well, this is so Josephson junctions. Of course, we always bias it with the DC current, but in the microwave experiments with microwaves, you also have an AC component. So let me put it this way: we have two regimes. Every Josephson junctions has two regimes. There is a static regime where if you look at your washboard potential, your phase is trapped in one of the minima in your Josephson energy, and there you don't have really this AC component. There is no voltage. The voltage only occurs where your phase is your phase particle, let's say on this washboard potential, starts to roll down. So if below the critical current there is no voltage, so you have zero voltage, and that's here. I think maybe I have some IV. So here there is no voltage. But when you go above the critical current, then you have the dynamic regime of your Josephson junction, and then you have an AC current, basically. So there is an AC component. What I'm doing is basically I'm irradiating the junction.
No. So the question from the chairman, what is you can probably do something with them, but how about producibility? How about how many times you can use?
And I send them to my colleagues, my collaborators in Tübingen, and sometimes it got stuck, in the DHL parcel delivery or whatnot, and it will decay pretty fast. But tungsten carbide that we print, it's pretty stable. Of course, we'd like to keep it clean, so usually we keep it in a desiccator somewhere. But even without capping, we can measure the microscope. With EBIT, you could just cap everything using an insulating layer of carbon. So you can just scan your beam over your structure and you deposit some carbon to protect your sample. I've seen actually people beam current and beam parameters. I've had 7 students on this project and they all, if they use the same beam parameters, they always get the same critical current and the same TC and same resistivity, which is I think one of the biggest strengths of this technique, which is a bit surprising.